last time we talked about the Clausius-Clapeyron equation. What I'd like to do this time is actually use the equation in some rather interesting examples in phase transitions. So one of the questions you might ask is, how much pressure would be required to lower the melting point of ice by 5 Celsius degrees? What we would need then is to use the latent heat of fusion of ice, which is 3.33 times 10 to the 5th joules per kilogram. And we would have to express the volume per kilogram of both ice and water. Well, the volume of ice is equal to 1.09 times 10 to the minus 3 cubic meters per kilogram. The volume of water is equal to 1.00 times 10 to the minus 3 cubic meters per kilogram. And so I can immediately use the Clausius-Clapeyron equation. That will allow me to calculate dP dt is going to be equal to 3.33 times 10 to the 5th joules per kilogram divided by the difference between these two volumes times the temperature, which original temperature 273.15 kelvins. And that would give me minus 1.34 times 10 to the minus 7 pascals per Kelvin, or 134 atmospheres per Kelvin. So it would take 134 atmospheres of pressure applied to water to depress its melting point by 5 Celsius degrees. So instead of melting at 0, melt at 5 minus 5. Oh, that's for 1 degree. So if I wanted to drop it by 5 degrees, I would have to multiply this by 5 for a total of 670 atmospheres of pressure to actually reduce the temperature, the melting point by 5 Celsius degrees. Do a similar kind of problem for water at the boiling point. Oftentimes when, if you are at high elevations, water boils too quickly to be able to cook something sufficiently. So oftentimes one will use a pressure cooker at high altitudes to try to, let's say, cook pasta or something like that. In order to do that, what the pressure cooker does is it essentially raises the boiling point of water from 100 to something higher, so that you're able to keep the water as water, not steam, and let's say boil your pasta, or boil your water for tea, whatever the case may be. So water boils at 100 degrees normally, 100 degrees Celsius, but suppose I want to raise the boiling point to 125 degrees Celsius. So note in this case, for vaporization problems, the volume of the vapor phase is so much larger than the volume of the liquid phase that we can essentially get rid of the delta V in the bottom of the Clausius-Clapeyron equation and just use the volume of the gas, because the volume of the water is just completely negligible compared to the volume of the gas. So immediately I can say dP dt is approximately L times heat of vaporization times the pressure divided by RT squared for liquid gas equilibrium. What I can do then, oh, and by the way, where does this come from? Well, all I'm doing then is I'm using the ideal gas law. So that being the case, I can replace my expression for volume by nRT over P. When I do that, I have an expression that looks like this. I can separate variables and write P final over P initial is equal to E. If I integrate both sides, E to the L over R, 1 over T initial minus 1 over T final. In our case, the initial temperature is 373 kelvins. The final temperature, we want to be 398 kelvins. The heat of vaporization for water is 2.26 times 10 to the 6th joules per kilogram. And R is just the universal gas constant, 8.31 joules per mole Kelvin. If you're careful with units here, by the way, you're going to change the heat of vaporization units from joules per kilogram. You want to use the expression L is 4.1 times 10 to the 7th, 10 to the 4th joules per mole. We want to use moles throughout the problem. The units of mole, of course, will cancel. If the initial pressure is 1 atmosphere, the final pressure, if I put all my numbers in, will turn out to be 2.28 atmospheres. So if you use a pressure cooker that can raise essentially more than double the pressure, you'll be able to raise the boiling point of the water so that you can cook whatever it is that you want to cook. So that's a nice example of the Clausius-Clapeyron equation. We have other examples. I think we're going to save them for a future lecture. We're going to talk about phase changes in liquid helium going from the normal liquid state to the superfluid state. We'll talk about the phase change of a conductor going to a superconductor at a low enough temperature. And I think those are worth spending time on because they're quite unusual compared to the usual phase changes that we talk about with melting and boiling and so on and so forth. So we'll talk about those topics in a future lecture. Thank you.